Picture this. You're swimming in the ocean on a perfectly calm day. The surface is like glass. There's no wind, no obvious waves. Yet you feel it. A steady, gentle, but absolutely undeniable pull. It's not a violent rip current trying to drag you under. It's a vast, river-like movement of the entire body of water, carrying you, slowly but surely, towards a horizon you can't quite see. You're not just in the water itself is going somewhere, and it's taking you with it. Now scale that up. Forget the ocean. Imagine our entire galaxy, the Milky Way, this sprawling, majestic city of 400 billion stars, 1 trillion planets, and enough dust and gas to build 1 billion more, is in the exact same situation. Our whole galaxy, along with 100,000 other galaxies in our cosmic neighborhood, is being pulled. We are all moving together at a speed that is frankly ludicrous. Over 600 kilometers a second. That's more than 2 million kilometers an hour. It's fast enough to get you from London to New York in about 8 seconds, if you could survive the trip. There's no visible engine. There's no obvious cosmic tow rope. There's just this relentless, silent, and incredibly powerful pull, dragging a colossal swath of the universe towards, well, that's the question, isn't it? For decades, we had no idea. We just knew we were moving, and we couldn't see what was pulling the strings. It was a mystery that pointed to something immense, something ancient, and something deeply hidden. This is not just a story about astronomy, it's a detective story on a cosmic scale. So, for our journey tonight into the weirdest parts of the universe, we're going to start right there. We're starting with the thing that has its hands on our home. Our anomaly number 1 is the Great Attractor. Let's begin with that speed. Try to really wrap your head around 2 million kilometers per hour. It's a speed so immense that it feels like a typo. When astronomers first started accurately measuring the movement of our galaxy relative to the background radiation of the universe, they got this number and had to check their math, because it implied a force of gravity so enormous that something truly monstrous had to be responsible. Something with the gravitational pull of 10,000 Milky Way galaxies at the very least. So the search was on. The hunt for this cosmic monster began in earnest in the 1970s and 80s. The first clue was the discovery of the cosmic microwave background, or CMB. Think of the CMB as a universal frame of reference. It's the afterglow of the Big Bang, and it's stationary everywhere. So if you can measure your movement relative to the CMB, you can find out your true speed through the universe. When we did that, we found we weren't just gently orbiting the center of our galaxy, we were on a rocket ship, and the whole rocket ship, the entire Milky Way, was blasting through space. The second clue was even stranger. When astronomers started mapping the motions of other galaxies, they found the same thing. Everything in our local supercluster, the Virgo supercluster, seemed to have an extra shared motion. It was as if the entire region of space was tilted and everything was flowing downhill. This wasn't the normal expansion of the universe, where everything moves away from everything else. This was a deviation. This was a specific, directed flow. All signs, all arrows were pointing in the same direction, toward a patch of sky in the southern hemisphere, somewhere behind the constellations of Triangulum Australe and Norma. In the mid-1980s, a team of astronomers who would become known as the Seven Samurai took on the monumental task of systematically mapping the motions of about 400 nearby galaxies to figure this out. It was slow, painstaking work. You have to find a galaxy, measure its light spectrum to determine its distance and velocity, and then repeat hundreds of times. But as they crunched the numbers, the picture became undeniable. All the galaxies in their survey, across a region of space more than 300 million light-years wide, were being drawn toward a single central point. They had found the source of the pull. They had found the location of the gravitational anomaly. They named it the Great Attractor, a name that sounds like it belongs to a final boss in a video game, and for good reason. Early estimates of its mass were terrifyingly large. The numbers suggested a concentration of matter so dense it defied explanation. The problem was, when they pointed their telescopes at that spot in the sky, they couldn't see anything nearly big enough to account for it. It was like feeling the heat of a bonfire, but seeing only a single flickering candle. The cause and effect were dangerously out of balance. The mystery wasn't solved. It had just gotten a whole lot deeper.
So where was it? Where was this galactic titan, this supercluster of all superclusters that was supposedly yanking on our part of the universe? Well, this is where the story gets a little ironic, a little spicy. It turns out the universe has a wonderful and deeply frustrating sense of humor. The Great Attractor was hidden in the one place in the sky that is almost impossible for us to see. It was hidden directly behind our own house. Imagine trying to describe a mountain range that lies on the other side of your city, but you're not allowed to leave your backyard, and your view is completely blocked by the sprawling city itself. That's the problem astronomers faced. The Great Attractor is located behind the plane of the Milky Way galaxy. This region of the sky is known as the zone of avoidance, or, if you want to be less dramatic, the zone of obscuration. It's a thick, foggy band that stretches across our sky, so dense with the stars, gas, and dust of our own galactic disk that it's like trying to look through a cosmic sandstorm. This dust doesn't just block visible light, it scatters it, making it incredibly difficult to get a clear picture of what lies beyond. For generations of astronomers, the zone of avoidance was just that, a zone to be avoided. It was a frustratingly opaque curtain drawn across a huge chunk of the cosmos. And as fate would have it, the single most significant gravitational structure in our corner of the universe was sitting right behind the middle of it. The universe was basically gaslighting us. It was like feeling a tug on your line, but being unable to see the fish because it's hiding directly under your boat. This led to all sorts of wild speculation. Was the Great Attractor made of something we couldn't see? Like a truly gargantuan concentration of dark matter? Was it a black hole so ancient and massive it beggared belief? The lack of visual evidence let imaginations run wild. For a while, the Great Attractor wasn't just a gravitational anomaly, it was a ghost. A powerful, invisible phantom shaping the fate of 100,000 galaxies, all while hiding from view. It was only with the advent of new technologies, telescopes that could see in infrared, X-ray, and radio wavelengths, that we were finally able to start peering through the cosmic smog. Peering through that smog was a revelation. It was like the fog slowly beginning to lift, revealing the true shapes of the mountains beyond. Using infrared surveys, which can cut through the dust more effectively, astronomers started to see them. Galaxies. Hundreds of them. Thousands of them. Right where the pull was strongest, there was indeed a massive cluster of galaxies, the Norma cluster, sitting about 220 million light-years away. Aha! Mystery solved, right? Here was a big pile of galaxies right where it should be. The problem was, when they calculated the mass of the Norma cluster based on the galaxies they could see, it still wasn't enough, not even close. It was a big cluster for sure, but it was like discovering a team of 10 strong men pulling on a rope that should require 1,000. The numbers still didn't add up. The Norma cluster was part of the answer, but it wasn't the whole story. The Great Attractor was bigger, more diffuse, and far more complex than a single cluster. This is a common theme in cosmology, by the way. You find what you think is the answer, only to realize you've just found a clue that points to an even bigger, more complicated question. It's a bit like Russian dolls, except every doll you open is somehow stranger and more unsettling than the last. The thing that was pulling us wasn't just the Norma cluster. The Norma cluster was just one of the most prominent features of a much larger superstructure. This is where the picture started to change. The idea of the Great Attractor as a single thing, a giant celestial body, began to fade. It was replaced by a new understanding, one that is less dramatic but infinitely more profound. The Great Attractor isn't an object, it's a place. It's the center of a gravitational valley. To understand this, we have to zoom out, even further than before, and look at the very architecture of our universe. What we thought was our home was just a suburb of a city we didn't even know existed. And that city has a name: Laniakea.
In 2014, a team of astronomers published a new map of our local universe. It wasn't a map of what you could see, but a map of where things were going. They used a massive database of galaxy motions to trace the gravitational contours of space, like a geographer mapping watersheds on Earth. A watershed is a region where all the water flows downhill into a common river or basin. On a cosmic scale, the equivalent is a basin of attraction, a region where all the galaxies are flowing downhill, gravitationally speaking, into a common center. Their work revealed, for the first time, the true extent of our home supercluster. It was vastly larger than we'd ever thought. This structure, which they named Laniakea, a Hawaiian name meaning immeasurable heaven, is breathtakingly huge. It's over 520 million light-years across and contains the mass of 100 million billion suns spread across those 100,000 galaxies, including our own Milky Way. And what we had been calling the Great Attractor for decades is simply the bottom of this immense gravitational valley. So the Great Attractor isn't a thing pulling us, it's the destination we're all flowing towards. The Milky Way isn't being dragged, it's sliding. All the galaxies of Laniakea, including us, are like raindrops on a vast, invisible window pane, slowly trickling down and merging into the puddle at the bottom. The pull is just gravity, acting on a scale so large it redefines what we consider our cosmic home. The Virgo supercluster, which we once thought was the pinnacle of our local structure, turned out to be just one small branch of the much larger Laniakea system. This discovery is both wonderfully elegant and a little deflating for the monster hunters. The cosmic horror story turned out to be a lesson in geography. But there's still a twist. Even Laniakea, as mind-bogglingly vast as it is not the end of the story. When we look at the motion of Laniakea itself, we see that the whole structure, the entire 520 million light-year wide basin, is also moving, being pulled by something even bigger, further away. It's being drawn toward another, even more massive concentration of galaxies known as the Shapley supercluster. It seems in the universe there's always a bigger fish, or in this case, a bigger gravitational valley to slide into. It's a journey that our galaxy has been on for billions of years, and one that will continue for billions more.
So we have our answer, or at least a much better version of it. The Great Attractor is not a phantom, but the gravitational center of our home supercluster, Laniakea, a home we didn't even know we had until a few years ago. It's a beautiful resolution to a decades-long detective story, but it leaves us with a certain feeling, doesn't it? A sense of our own motion, our own cosmic trajectory. We are not static, we are not aimlessly adrift. We are part of a grand, silent, and incredibly slow stampede toward a point on a map we've only just drawn.
let's leave Laniakea behind. Our journey from now on is a journey of contrasts. We have just explored an anomaly defined by its immense, overwhelming presence, a place of such profound gravitational power that it shapes the destiny of our entire galactic neighborhood. It is the ultimate cosmic something. Now we are going to travel to its polar opposite. We are going to a place defined not by what is there, but by what isn't. A place where the great cosmic web of galaxies seems to have been erased. A hole in the universe so vast, so empty, and so profound that it makes the blackness of normal space look crowded. We are leaving the grand, bustling metropolis of Laniakea and heading for the universe's most desolate and abandoned wasteland. Our anomaly number 2 is the Bootes Void. Imagine that map of the universe we talked about before, with its glowing filaments and massive walls of galaxies. It's a rich, intricate tapestry. Now, imagine someone took a giant pair of scissors and cut a hole out of it. A circular hole, hundreds of millions of light years across. That's our destination. To get there, we first look toward a familiar shape in our northern sky, the constellation Bootes, the herdsman. It's an ancient, comforting pattern, but we are looking past it, into the deep, dark space behind it. It's here that in 1981, astronomers found something so unsettling it forced them to rethink how the universe was even put together. They found, for all intents and purposes, nothing at all.
The story of the discovery of the Bootes Void is a perfect example of science delivering a result so weird it sounds like a mistake. In the late 1970s and early 80s, astronomers like Robert Kirshner and his team were undertaking the tedious but vital work of creating a three-dimensional map of the universe. They would point a telescope at a faint smudge of a galaxy, measure its redshift, the stretching of its light due to the expansion of the universe, and use that to calculate its distance. Point, measure, calculate, repeat. Over and over and over. Through this process, they were confirming that the universe was lumpy, with galaxies clumping together in clusters and filaments. Their work was going as expected, but then they started mapping a specific region in the direction of the Bootes constellation, and their rhythm was broken. They would point the telescope at a patch of sky where they expected to find a galaxy, and they would find nothing. Now, this isn't immediately alarming. Space is big. Maybe you just picked an empty spot. So you adjust your aim. You point the telescope somewhere nearby, and you find nothing again. You check your instruments. Are they working? Is something wrong with the detector, the telescope, the math? You run diagnostics. Everything comes back green. The equipment is fine. So you try again. You point it at another spot, and again. Nothing. The silence from the cosmos is deafening. This went on for weeks, then months. The team kept surveying this one large patch of sky, a region where their models predicted they should find hundreds, if not thousands, of galaxies. And their senses came back almost entirely empty. The feeling must have been deeply unnerving. It's like being a biologist, taking a survey of a lush jungle and suddenly stumbling upon a perfectly circular patch of land, miles wide, with no trees, no animals, no insects, no life. Just bare, sterile rock. It violates every expectation. It shouldn't be there. It's a profound and disturbing wrongness in the fabric of reality. That's what they found. A hole in the universe.
So, just how big and how empty is this hole? The numbers are genuinely difficult for the human mind to process, but let's give it a try with an analogy. Picture the Milky Way galaxy, our home. 400 billion stars, nebulae glowing with the birth of new suns, planets, asteroids,
everything. It's about 100,000 light-years across. Now, let's shrink that entire magnificent structure down. Let's make it the size of a small green pea. Got that pea in your hand? Okay. Now, on that same scale, the Boötes void is a sphere about 1,000 feet or 300 meters in diameter. It's a bubble the size of a sports stadium. Now imagine standing in the center of that colossal empty stadium. If the universe had its normal expected density, that stadium should be filled, absolutely packed, with more than 10,000 other peas. It would be a giant ball pit of galaxies. But it isn't. The Boötes void is not full. When you stand in the center of that stadium-sized void and look around, you see almost nothing. The entire volume, where thousands of galaxies should be, contains only about 60 peas in a space built for 10,000. It is the loneliest place in the entire observable universe. Its official name is the Boötes void, but it has earned a much more fitting nickname, the Great Nothing. The sheer emptiness is one thing, but its shape is another. It's startlingly spherical. It's a bubble. This shape was a huge clue for astronomers trying to figure out what could possibly have caused this cosmic bald spot. One of the earliest, most dramatic ideas was that some kind of cataclysmic, universe-altering explosion had occurred, blowing all the matter outwards like a cosmic bomb. But the energy required for that would be unthinkable, and there's no evidence of such a violent event. The real answer, scientists now believe, is just as epic, but far less explosive. It's a story not of destruction, but of construction. The void wasn't blown out, it was squeezed out.
The leading theory for how the Boötes void formed is a process that sounds gentle but is cosmologically relentless. It's all about bubbles. Think back to the early universe. It was a much smoother, more uniform place, but it wasn't perfect. There were tiny quantum fluctuations, making some areas infinitesimally denser than others. Gravity, ever the patient opportunist, got to work. The slightly denser regions started pulling in more matter, growing into the seeds of galaxies and clusters. This means that the slightly less dense regions became even emptier. These were the proto-voids, the first little pockets of nothingness. Now imagine a sink full of soap bubbles. What do? The smaller bubbles merge, combining their volume to create larger, more stable bubbles. The dividing walls between them pop and retreat. Over billions of years, that's what scientists believe happened in space. The smaller voids, pushed by the gravity of the growing galactic filaments around them, drifted together. They merged. Their shared emptiness coalesced, pushing the galaxies and matter into the great walls and filaments that define the boundaries of the void. The Boötes void, then, is the result of a particularly successful series of mergers. It's a supervoid. It's what happens when dozens or hundreds of smaller voids combine to form one truly monolithic bubble of empty space. It's not a scar. It's a masterpiece of cosmic architecture built from nothing at all. It's an elegant theory, and it fits the observations well. But frankly, understanding the process does very little to diminish the sheer unnerving spectacle of the place itself. Let's go back inside for a moment. Let's visit one of those few lonely galaxies that exist within the void. We can call them the void dwellers. There are about 60 of them that we've found so far, and oddly enough, they seem to be arranged in a strange tube-like structure running through the middle of the void. Why? Nobody knows. It might be the last wisp of a galactic filament that was there before the voids merged around it. A final, stubborn thread in an unraveling tapestry. Or it might be something else entirely. It's just another layer of strangeness.
Imagine being an astronomer on a planet in one of those 60 galaxies. Let's call it Void Galaxy X. You grow up, you look up at your night sky. What do you see? From Earth, we are spoiled. Our sky is rich with the light of our own galaxy and, with a good telescope, the faint smudges of our neighbors. But from Void Galaxy X, the view would be breathtakingly barren. Your own galaxy would be a brilliant band across the sky, just like our Milky Way. But beyond that, the darkness would be near total, absolute. For us, the Andromeda Galaxy is a naked-eye object under the right conditions. For a civilization in Void Galaxy X, the nearest major galaxy would be so far away, across tens of millions of light-years of sheer nothingness, that it might be completely invisible until they developed extremely advanced telescope technology. Think about the philosophical and scientific implications. For most of their history, they would be utterly convinced that they were the only galaxy in the entire universe. All their myths, their religions, their science would be built on the foundation of ultimate, absolute solitude. There would be no evidence to the contrary. Then, one day, an astronomer builds a new, powerful observatory. She points it at the deepest, darkest part of their sky, and after a long exposure, she sees it. A faint, impossibly distant smudge of light, and then another, and another. She would be the first person in her civilization's history to realize they aren't alone. She would have discovered that their entire universe was just an island in a vast, empty ocean, and beyond that ocean, there were other shores. Floating here in the center of the Great Nothing gives you a sense of cosmic perspective that is both terrifying and humbling. It reminds you that the universe isn't a single uniform thing. It's a place of wildly different environments. There are bustling galactic superhighways, and there are these vast, silent, forgotten country roads. The Buttes Void is the ultimate cosmic countryside. It's a place where the silence is so profound, you can almost hear the faint, distant hum of the rest of existence happening somewhere else, a very, very long way away.
We leave the Buttes Void behind, an island of profound emptiness. It's a place defined by what isn't there, but it teaches us a fundamental lesson. The universe is not homogeneous. It has structure, grain, and character, and its biggest secrets are often hidden not in the things we see, but in the patterns and absences. Now, we're going to look at another, even more ancient absence, but this time it's not an absence of matter, it's an absence of heat. We are going to travel back in time to look at the very first light the universe ever produced. This is the cosmic microwave background, the CMB. Think of it as the universe's baby picture. It's the faint, fading afterglow of the Big Bang, a wall of light that was emitted when the cosmos was just 380,000 years old. Before this, the universe was an opaque, hot soup of plasma. But at this moment, it cooled just enough for atoms to form, and for light to finally travel freely. That light has been traveling ever since, and it fills every cubic centimeter of space today. When we look at this light, it is astonishingly, almost miraculously uniform. The temperature of the CMB is the same everywhere we look, down to a few parts in 100,000. This uniformity is a cornerstone of modern cosmology. Those tiny, minuscule fluctuations in temperature were the seeds, the gravitational starting points, around which all the great structures, the voids, the filaments, the great attractors, eventually grew. It's a beautiful, elegant, and almost perfectly painted canvas. Almost.
Because in this near-perfect picture of the infant universe, there is a stain, a blemish, a patch of the sky that is significantly, uncomfortably colder than it has any right to be. It's a smudge on the baby picture, a fingerprint on the masterpiece. It's another void, but of a completely different kind. Our anomaly number 3 is the CMB cold spot. Located in the direction of the southern constellation Eridanus, the river, this isn't a place you can fly to. It exists on the very edge of the observable universe, imprinted on that wall of ancient light. It's a massive patch of sky, many times wider than the full moon, where the temperature of that primordial afterglow is just a little bit lower than everywhere else. It might not sound like much, but in a picture this uniform, a deviation this large is the cosmic equivalent of a scream in a library.
The discovery of this anomaly was a slow burn realization, a product of increasingly precise observations. For years, our view of the cosmic microwave background was blurry, like a photograph taken with a shaky hand. But in 2001, NASA launched the Wilkinson Microwave Anisotropy Probe, or WMAP. Its mission was simple: stare at the entire sky for years and produce the most detailed map of this ancient light ever created. Imagine its job. It orbits the Sun, 1 million miles from Earth, shielded from our planet's heat and noise. Day after day, it patiently scans the faint microwave hiss coming from every direction, measuring tiny temperature differences with incredible sensitivity. After years of this patient work, scientists began to assemble the data into a single, all-sky map. It was a triumph, a stunning oval-shaped image of the infant universe, speckled with tiny hot spots in red and tiny cold spots in blue. It confirmed our theories of cosmology with breathtaking accuracy. But as they analyzed this beautiful map, one spot kept drawing their attention. Down in the bottom right quadrant, there was a blue patch that was just bigger and bluer. While most of the fluctuations were small and randomly scattered, as you'd expect, this one was an outlier, a big, brooding, cold splotch that stood out from the rest of the noise. The first reaction, as always in science, was skepticism. It must be an error, a glitch in the instruments, contamination from some foreground object, or maybe just a statistical fluke. If you flip 1 million coins, you're bound to get a weird streak of heads eventually. But then, the European Space Agency launched the Planck satellite. It was even more sensitive than WMAP. It stared at the sky for even longer, and it produced a map of the CMB with even higher fidelity. And when the first Planck map was released in 2013, everyone looked to that same spot in Eridanus. The verdict was undeniable. The cold spot was still there. It was real. It wasn't a glitch. It was a genuine feature of our universe. The scream in the library was not a mistake. Something had happened there. And the most obvious explanation was, funnily enough, linked directly to our last anomaly. The theory was simple. What if the light from that part of the sky had to travel through another great nothing?
So how can a patch of empty space make ancient light appear colder? It's a slightly weird bit of physics, but the concept is quite intuitive. It's called the integrated Sachs-Wolf effect, but let's call it the cosmic pothole effect. Imagine light as a tiny marble rolling across a flat rubber sheet. This is space-time. Now, a big, massive object, like a cluster of galaxies, creates a dip in that sheet, a gravity well. As the marble of light rolls into the well, it picks up energy and speed. It gets a little bit bluer, a little hotter. Then, as it climbs back out the other side, it loses that exact same amount of energy, and it returns to its original state. For a normal patch of space, the net effect is zero, but our universe is expanding, and that changes things. Now imagine the light marble rolling into a gravity well, but while it's inside, the universe expands. The well itself gets stretched out, becoming shallower. So when the light climbs back out the other side, it doesn't have to climb as steep a hill as the one it rolled down. It leaves with a little bit of extra energy. It gets a tiny energy boost, a blue shift. The opposite happens in a void. A void isn't a well, it's more like a hill, a region with less gravity than average. So as light enters a void, it has to climb a gravitational hill, losing energy and getting redder, or cooler. While it's crossing the void, the universe expands, and the hill itself flattens out. So when the light rolls down the other side, it doesn't get all its energy back. It leaves the void with a net energy loss. It has been permanently, slightly, cooled. It's hit a cosmic pothole. So the leading theory for the CMB cold spot was born. What if there is a colossal supervoid, maybe even bigger than Boötes, sitting right between us and that part of the CMB? The ancient light from the Big Bang would have to travel through this billion light-year wide pothole on its 13.8 billion-year journey to us. In doing so, it would lose a tiny bit of energy, making that entire patch of the sky appear colder to our satellites. It was a perfect, elegant explanation that neatly tied together two of the universe's biggest mysteries. There was only one problem. When we went looking for this supervoid, the evidence was debatable.
Finding a supervoid isn't as easy as it sounds. You can't see emptiness. You can only infer it by meticulously counting the galaxies in that direction and proving that there are far fewer of them than there should be. Several astronomical surveys have done just that, pointing their telescopes toward the cold spot to conduct a census of the region. The results have been maddeningly ambiguous. Yes, the region does seem to be underdense. There are fewer galaxies there than in an average patch of sky. Some studies have even given this region a name, the Eridanus supervoid. It seems to be a real thing. But here's the catch. It doesn't seem to be empty enough. The void we've found is large, but it's not the Great Nothing Part 2. It's just a bit sparse, like a party that's a little poorly attended, not a completely empty ballroom. When cosmologists run the numbers, the Eridanus supervoid, as we currently measure it, is only capable of explaining about 10 to 20% of the coldness of the cold spot. It can't account for the whole thing. This has led to a fierce and ongoing debate in the astronomical community. Some scientists argue that our surveys are incomplete, that we're missing a lot of small, faint galaxies, and that the void is actually much emptier than it appears. Others argue that the void theory is only part of the puzzle, and that something else must be contributing to the coldness. And then there's the third and most statistically likely option, the one that every scientist has to consider, but nobody really likes because it's so unsatisfying. Maybe there is no mystery. Maybe the cold spot is just a fluke. In any random dataset, there will be outliers. If you map the heights of every person on Earth, someone has to be the tallest. If you look at a perfectly random pattern of dots, some areas will just happen to look like they form a cluster. Maybe the cold spot is just that, the 1 in 1,000 statistical fluctuation that was bound to show up somewhere. The universe rolled the dice, and this patch of sky just happened to come up cold. It's a perfectly valid scientific explanation, and it's also incredibly boring, which for our purposes might be perfect. But it's not the only other option.
When a clean explanation like a supervoid doesn't quite fit, and the "it's just a random fluke" explanation feels like giving up, you open the door to the really exotic stuff. This is where scientists get to be creative, to push the boundaries of known physics and ask some truly wild what-if questions. And for the CMB cold spot, the what-ifs are spectacular. One of the most mind-bending theories is that the cold spot is not a feature in our universe, but rather the result of an interaction with another universe. This idea comes from string theory and concepts of a multiverse.
The theory goes something like this. Our universe is just one bubble or membrane floating in a higher dimensional space, along with countless other bubble universes. And every now and then, these bubbles might bump into each other. If another universe had a close encounter with ours in the distant past, it could have left a mark. The gravitational jostling could have warped space-time in that region, creating a sort of cosmic bruise. The cold spot, in this scenario, would be that bruise. It would be the fossilized remnant of a collision between worlds on a scale we can barely comprehend. It's a theory that is equal parts thrilling and completely untestable with our current technology, which puts it firmly in the realm of delicious speculation. It suggests our universe might not be so alone, but that its neighbors are a bit careless. Other exotic theories propose that the cold spot is a window into some kind of strange, new physics. Perhaps it's a texture, a kind of defect in space-time left over from the phase transitions of the very early universe, like a flaw in a diamond. Or maybe it's a gateway to somewhere else entirely, a topological defect that connects our universe to, well, who knows? So what is it? A giant undiscovered hole in space? A 1 in 1,000 statistical accident? Or a bruise from a brawl with a parallel universe? We still don't know. The CMB cold spot remains a tantalizing open question. It's a permanent, cold fingerprint on the oldest thing we can see, a reminder that the universe's baby picture has a story we haven't fully deciphered yet. Now, let's pull our gaze away from the edge of time and space. Let's come all the way back home, into our own Milky Way galaxy. From the biggest, most ancient anomaly on the map, we are going to zoom in on a single, solitary, and utterly insignificant-looking star. A star that decided one day to start behaving so strangely that it made a collision between universes look like a reasonable explanation. Our anomaly number 4 is Tabby Star.
To find this star, we look toward the constellation Cygnus, the Swan. It's a star officially known as KIC 8462852, a dry, technical name that gives no hint of its bizarre personality. It's about 1,500 light-years away, a fairly normal F-type star, a little bigger and hotter than our Sun. For all intents and purposes, it should be a stable, well-behaved member of the galactic community. But it isn't. Our story begins once again with a planet-hunting telescope, the Kepler Space Telescope. We've talked about its mission before, to find exoplanets by watching for the slight periodic dimming of a star as a planet passes in front of it. This is called the transit method. It's a numbers game. Kepler stared relentlessly at a patch of sky containing about 150,000 stars, measuring their brightness with incredible precision every 30 minutes for 4 straight years. The vast majority of this data is, frankly, boring. It's just star after star shining steadily, a flat line. Occasionally, you get a beautiful, tiny U-shaped dip in the light repeating like clockwork. That's a planet, a triumphant discovery. But the data from KIC 8462852 was not a beautiful U-shaped dip. It wasn't triumphant. It was a mess. The data was so messy, in fact, that Kepler's automated algorithms designed to find the neat transits of planets just threw it out. It was classified as an anomaly, an error, and ignored. The only reason we know about this star today is because of human eyes. The data was handed over to a citizen science project called Planet Hunters, where volunteers could look through Kepler's rejected data to see if the computers had missed anything. And one day, a few of these volunteers stumbled upon KIC 8462852. They flagged it. They said, "We don't know what this is, but it is not normal."
They had no idea. They had just found the most mysterious star in the galaxy.
So what did they see? What did this star's light curve actually look like? Well, a normal planetary transit might dim a star's light by, at most, 1%. It's a tiny, subtle dip. The data from Tabby Star, named after the lead author of the paper that investigated it, Tabitha Boyajian, showed something else entirely. It showed dips in brightness that were colossal, chaotic, and completely unpredictable. In one event, the star's light dimmed by 15%. A few years later, it dimmed by a staggering 22%. To put that in perspective, even a gas giant the size of Jupiter passing in front of our Sun would only block about 1% of its light. To block 22% of this star's light, you would need an object 1,000 times the area of the Earth. This wasn't a planet. This was something else. Something huge. And it wasn't just the depth of the dips, it was their shape. They weren't the clean, symmetrical U-shape of a solid, spherical planet. They were jagged, asymmetrical, and erratic. Some were sharp and deep, some were broad and shallow. The star's brightness would flicker and plunge over days or weeks, with no discernible pattern. It was not the light curve of a star with a planet. It was the light curve of a star that was being intermittently and clumsily obscured by something. The first paper on the star, published in 2015, did an admirable job of trying to find a natural explanation. The scientists went through every plausible scenario they could think of. Let's walk through them because the process of eliminating them is what makes this story so compelling. First idea, a massive asteroid belt. Maybe there was a huge collision between planets in that system that created a vast field of debris. The problem is that such a collision would generate a lot of fine dust, which would get heated by the star and glow brightly in infrared light. When we looked at Tabby Star with infrared telescopes, we saw no such glow. The debris, whatever it is cold. Strike one.
Okay, so if it's not a hot cloud of recently smashed up planets, what else could it be? Idea number 2, a huge swarm of comets. This became the leading natural explanation for a while. The idea is that maybe another star passed close to Tabby's star in the distant past, disrupting a massive cloud of comets at the edge of its system, its version of our Oort cloud. This could have sent a giant swarm of them tumbling toward the inner system, and we just happened to be looking at the star as this cometary apocalypse is unfolding. This explanation is a bit better. Comets are mostly ice, not rock, so they wouldn't create the same kind of hot infrared dust signature. A huge, clumpy, disorganized swarm of them could, in theory, create the kind of deep, irregular dips in starlight that we see. It's a plausible, if incredibly dramatic scenario. The universe is a violent place. These things can happen. But there's a problem of scale. To block 22% of the star's light, you don't just need a few comets. You would need a truly biblical plague of them. Tens of thousands of massive comets, all marching in formation, all arriving at the same time. The sheer number required is so high that it strains credulity. While it's not impossible, it would require a level of cosmic coincidence that makes scientists uncomfortable. It would mean we are witnessing an event that is exceptionally rare at the exact right moment in time. It's a possible answer, but it feels like a stretch, a bit too convenient. Then there are theories involving the star itself. Maybe the star is just weird. Maybe it has some unknown internal process that causes it to dim and brighten erratically. The problem here is that its stellar type, an F star, is typically very stable. They're not known for this kind of wild variability. And the patterns of dimming don't match any known mechanism of stellar physics. It's not behaving like any star we've ever seen. So you have a mystery. The debris isn't hot enough. A swarm of comets seems unlikely. The star itself seems fine. You have systematically worked through every reasonable natural explanation you can think of, and none of them quite fit. They all require you to believe in something extremely unlikely. It was at this point that one of the paper's authors, Jason Wright, mentioned another possibility. A possibility that was so outlandish, it was only proposed because everything else had failed. The possibility that what we were seeing wasn't natural at all.
The suggestion was this: what if the thing obscuring the star wasn't a cloud of rocks or a swarm of comets, but a swarm of artifacts? What if we were seeing evidence of a massive structure or a collection of structures built by an intelligent civilization and placed in orbit around the star? This is the alien megastructure hypothesis. And before you roll your eyes, it's important to understand why it was even put on the table. It wasn't proposed out of a desire to find aliens. It was proposed out of a process of elimination. The data from Tabby's star is so strange that it defies every natural explanation we have. The dips are deep, which means the obscuring object is large. The dips are not infrared hot, which means the object is not a natural dust cloud from a recent collision. The dips are irregular and aperiodic, which means it's not a simple planet or group of planets. So, what kind of object could be large, cold, and have a complex, irregular shape? Well, a vast orbiting structure would fit that description perfectly. The concept is often linked to the idea of a Dyson sphere, or more plausibly, a Dyson swarm. This is a hypothetical megastructure that an advanced civilization might build to harvest a huge percentage of its star's energy. Instead of a solid shell, it would likely be a massive cloud of individual solar collectors and habitats, all orbiting the star in a thick, dense swarm. Such a swarm would block a lot of light. Its components would have complex shapes, leading to irregular dimming events. And because they would be designed to absorb energy, not radiate it away uselessly as heat, they wouldn't produce a strong infrared signal. It checked all the boxes in a way that the comets and dust clouds didn't. The hypothesis wasn't, it's aliens. The hypothesis was, the data is consistent with what we might expect from an artificial megastructure. It was a stunning and terrifying conclusion to reach. For a brief moment, it seemed like the most plausible explanation on the table, however improbable it sounded.
The alien megastructure hypothesis, as you can imagine, caused a massive sensation. The media loved it. The public loved it. The Search for Extraterrestrial Intelligence, or SETI, Institute pointed its radio telescopes at the star, listening for any signals that might betray an intelligent source. The result? Nothing. Total radio silence. That doesn't disprove the theory, of course. The civilization could be long dead, leaving their structures to orbit like cosmic ghosts. Or they might simply not use radio. Or maybe they're just not talking to us. In the years since the initial discovery, more data has come in. We've observed the star with more telescopes, and we've seen more strange dimming events. One of the most significant new findings is that the dimming seems to be color-dependent. That is, the star's blue light is blocked more effectively than its red light. This is a crucial clue. Why? Because normal, solid objects, like a planet or a giant spaceship, should block all colors of light equally. But very fine dust, not the hot dust from a collision, but fine, cold, interstellar dust is different. Dust particles are very good at scattering shorter wavelength blue light while letting longer wavelength red light pass through more easily. It's the same reason our sky is blue and our sunsets are red. This discovery has swung the pendulum of opinion back towards a natural explanation. The current leading hypothesis is no longer a swarm of comets, but a cloud of circumstellar dust. Not a hot, dense cloud from a recent impact, but perhaps a fine, diffuse cloud being drawn in from the interstellar medium or being shed by the star itself in some unknown way. Or maybe there are exocomets after all, but they are producing this fine dust as they disintegrate. It's a much less dramatic theory than a Dyson swarm, but it seems to fit the data better. However, it's still not a perfect fit. The source of this dust and why it's clumpy enough to cause such massive dips remains an open mystery. Tabby's star has calmed down a bit from its most extreme dimming events, but it continues to flicker and fade unpredictably. It remains an anomaly. It forced us to seriously consider, for the first time, what the observational signature of alien technology might actually look like. And it serves as a stunning reminder that a single, unassuming star can still hold a puzzle that stumps us completely.
We leave Tabby's star behind, a single, flickering candle in the cosmic dark that continues to defy a simple explanation. It's a mystery of light, of what we can see. But some of the universe's greatest puzzles are found not in what we can see, but in what we can hear. I'm speaking metaphorically, of course. Space is a vacuum. There is no sound. But for over 80 years, we have been listening to the cosmos with radio telescopes. Instead of collecting visible light, these giant dishes collect radio waves, a much lower energy form of light. If our eyes see the universe as a grand, silent film, radio telescopes provide the soundtrack. And for most of its history, that soundtrack has been a gentle, predictable hiss. It's the background static of distant pulsars, the steady hum of ancient galaxies, the faint echo of the Big Bang itself. It's a calm, soothing, and largely unchanging score. Until it wasn't. Imagine you are a radio astronomer on the night shift. You're monitoring the data coming in from a giant telescope, which mostly consists of long, boring charts of this gentle static. Then, for less time than it takes you to blink, a single, impossibly loud spike appears on your screen. A burst of radio energy so powerful it outshines entire galaxies, but it lasts for only a few milliseconds before vanishing completely, without a trace. It's the cosmic equivalent of a gunshot in a quiet night. You check the equipment, you check the time, you look for a cause. A passing satellite? A faulty microwave oven in the observatory's kitchen? But you find nothing. The signal was real. It came from deep space, and it's gone. For years, this was the state of things. Astronomers were catching fleeting glimpses of these inexplicable signals, so brief and so powerful they bordered on unbelievable. They were like cosmic apparitions. Our anomaly number 5 is this phantom signal. We're hunting fast radio bursts.
The story of the first fast radio burst, or FRB, is a lesson in scientific discovery and frustration. It was found in 2007, not in real time, but in archival data from 2001. A professor at West Virginia University, Duncan Lorimer, had tasked his student, David Narkovich, with combing through old data from the Parkes radio telescope in Australia. It was grunt work, sifting through mountains of old observations, looking for new pulsars. And then, Narkovich found it. A single, brilliant burst of radio waves that lasted for less than 5 milliseconds. It was absurdly strong, but so brief it could have easily been dismissed as a glitch. The key, however, was its dispersion. We'll get to what that means in a moment, but it's a property that told them the signal had traveled a vast distance from far outside our own galaxy. They had found something extraordinary. They published their findings, and the Lorimer burst officially kicked off a new field of astronomy. And then, nothing. For years, other astronomers looked, but couldn't find any more of these bursts. The whole thing started to feel like a fluke. The situation got even more confusing with the discovery of peritons. The same Parkes observatory that found the first FRB started detecting other, similar-looking bursts. But these ones were strange.
They seemed to happen more during the daytime, and they appeared to hit all of the telescope's receivers at once, suggesting they were coming from somewhere nearby, not from deep space. The mystery of the peritons went on for years, casting doubt on the entire phenomenon of FRBs. Were they all just some kind of local interference? The puzzle was finally solved in 2015, and the answer is one of the all-time great moments in scientific troubleshooting. The source of the peritons was traced to microwave ovens in the facility's kitchen. It turned out that if you open the microwave door prematurely while the magnetron was still powering down, it would release a short, powerful burst of radio waves that perfectly mimicked an astrophysical signal. The mystery wasn't aliens, it was impatient astronomers wanting their lunch. Once the microwaves were fixed, the peritons vanished. This allowed scientists to confirm that the real FRBs, like the Lorimer burst, were genuinely cosmic, and the hunt began again in earnest.
So what makes these bursts so special? It comes down to two things: power and dispersion. First, the power. In the few milliseconds that an FRB exists, it can release as much energy as our sun does in an entire day. Some of the more powerful ones release as much energy as the sun does in a year. Let that sink in. A year's worth of solar energy compressed into a flicker of radio waves that is 1,000th of a second long. Whatever is creating these signals has to be one of the most energetic and violent processes in the entire universe. Second, and more importantly, is the dispersion. This is the key that unlocks their secrets. The space between galaxies is not a perfect vacuum. It's filled with a very thin, tenuous plasma of electrons. When a radio burst travels through this plasma, it gets smeared out. The higher frequency radio waves travel slightly faster than the lower frequency ones. So by the time the signal reaches us, it's no longer a single sharp spike. The high frequency waves arrive first, followed milliseconds later by the low frequency waves. Think of it like a group of runners. They all start the race at the exact same moment, but the faster runners will finish slightly ahead of the slower ones. By measuring the time delay between the arrival of the different frequencies, astronomers can calculate exactly how much stuff the signal had to travel through. This dispersion measure is like a cosmic ruler, and the dispersion measures for FRBs were huge, way too large for them to have come from inside our own galaxy. They were proof that these signals were crossing millions or even billions of light years of intergalactic space. They were coming from the distant universe. So now you have a profile of your culprit. It's an object or event that can produce more energy in a millisecond than our sun produces in a day, and it's located in a galaxy far, far away. This immediately rules out most normal stars. Even a supernova, one of the most violent events we know of, doesn't quite fit the profile. A supernova unfolds over weeks and produces light across the whole spectrum. These bursts were pure radio, and they were gone in an instant. The universe had thrown another impossible puzzle at us. The immense challenge with FRBs was finding them. It was like trying to photograph a specific bolt of lightning in a thunderstorm that covers the entire globe. You don't know when or where the next one will strike. For years, we were finding them purely by accident, in old data. It was serendipity, not science. To make real progress, we had to get better at catching them in the act. The problem is twofold. Most radio telescopes have a very narrow field of view. They look at a tiny patch of the sky, like looking through a drinking straw. The odds of a random millisecond-long burst going off in that tiny patch while you happen to be looking are astronomically low. Second, even if you do catch one, it's gone instantly. You can't go back and look at it again to study it more carefully. It's a one-and-done event. This led to a period of intense frustration. Dozens of FRBs were detected, but they were all solitary events from all over the sky. We knew they were happening, but we couldn't study their source. We couldn't even figure out which galaxies they were coming from. It was like getting mysterious postcards from all over the world, but with no return address. We knew someone was out there, but we had no idea who or where they were. To solve this, a new type of telescope was needed, one with a huge field of view that could watch a large chunk of the sky all the time. Enter CHIME, the Canadian Hydrogen Intensity Mapping Experiment. Located in British Columbia, CHIME is a radical design. It has no moving parts. It's just 4 100-meter-long half-pipe cylinders of wire mesh, looking like a giant skateboard park. It stares straight up, and as the Earth turns, the sky drifts over it. With its massive computing power, CHIME can watch a huge swath of the sky simultaneously, and it is an FRB-catching machine. Since it went online in 2018, CHIME has detected over 1,000 FRBs, dramatically increasing our catalog. It was a revolution, but even CHIME couldn't solve the biggest problem. If the bursts don't repeat, you can't pinpoint their origin. The real breakthrough, the clue that finally cracked the case open, came not from a new telescope, but from an old friend. One of the bursts decided to talk back.
In 2012, a burst was detected at the Arecibo Observatory in Puerto Rico. It was cataloged as FRB 121102. Nothing special about it at first. But then, in 2015, astronomers decided to point their telescopes back at that same patch of sky, just in case. And they caught another burst. And then another. And another. This was it. The game changer. They had found the first repeater. This was a monumental discovery for 2 reasons. First, it proved that whatever creates these bursts, it isn't always a cataclysmic self-destructive event. If the source can burst multiple times, it must survive the process. This immediately ruled out scenarios like 2 neutron stars colliding, which was a leading theory. That's a one-time only show. The source of FRB 121102 was a durable engine of some kind. Second, and more importantly, because it repeated, astronomers could stare at that one spot in the sky for hours, days, weeks, waiting for it to perform. And by using multiple radio telescopes around the world in unison, they could use interferometry to triangulate its position with incredible precision. In 2017, they found it. They pinpointed the source of FRB 121102 to a specific location. It was coming from a tiny, faint, star-forming dwarf galaxy over 3 billion light-years away. Finally, we had a return address on one of the postcards. We knew the kind of neighborhood these things lived in, and it was a strange one. A small, messy galaxy full of hot, young, massive stars. The kind of place where you find lots of supernovae and other high-energy phenomena. This was a crucial clue. It suggested that FRBs are linked to the life and death of massive stars. Since then, we found a few dozen other repeaters, though most of the thousands of FRBs we've seen have still only ever flashed once. But the repeaters gave us the clues we needed to zero in on a prime suspect. The evidence started to point toward one of the most extreme and violent objects in the entire cosmic zoo, an object called a magnetar.
So what on earth is a magnetar? To understand it, you first have to understand a neutron star. When a massive star, much bigger than our sun, runs out of fuel, it collapses under its own gravity and then explodes in a supernova. What's left behind is the star's incredibly dense, crushed core. This is a neutron star. It's an object with the mass of 1.5 suns squeezed into a ball no bigger than a city, about 20 kilometers across. A single teaspoon of neutron star material would weigh about 1 billion tons. They are the densest objects in the universe, aside from black holes. Now, take that already ridiculous object and give it a magnetic field. Not just any magnetic field.
When the star's core collapses, its original magnetic field gets compressed and amplified to insane levels. A typical neutron star might have a magnetic field 1,000,000,000,000 times stronger than Earth's. But a magnetar? A magnetar is a special kind of neutron star. It is a true monster. A magnetar's magnetic field is another 1,000 times stronger than that. It is a 1,000,000,000,000 times the strength of Earth's magnetic field. It is so powerful it defies all earthly analogies. It is strong enough to rip you apart at the atomic level from 1,000 kilometers away. It is so strong it actually distorts the shape of the star itself, causing the solid crust to buckle and crack, leading to starquakes. These starquakes are incredibly violent. As the crust cracks, the magnetic field lines, which are trapped within the star, can suddenly reconfigure themselves. They snap and reconnect in a new shape, and in the process, they release a truly biblical amount of energy. For a long time, this process was the leading theory for what might cause FRBs. A starquake on a magnetar could easily release a sun's worth of energy in a millisecond, in the form of a focused blast of radio waves and other high-energy particles. The theory was perfect. Magnetars are formed from massive stars, explaining why FRB 121102 was found in a star-forming galaxy. Their starquakes could be a recurring event, explaining the repeaters. It all fit. But for years, it was just a theory. There was no direct, conclusive proof. We had never actually seen a magnetar produce an FRB. The suspect was in the lineup, but we hadn't caught them with the smoking gun. That all changed in April of 2020.
On April 28, 2020, something remarkable happened. A magnetar, located just 30,000 light-years away, inside our own Milky Way galaxy, decided to throw a tantrum. This magnetar, known as SGR 1935+2154, was being monitored by several X-ray and gamma-ray space telescopes, and they saw it erupt in a massive flare. This was typical magnetar behavior, but at the exact same moment, two radio telescopes on Earth, CHIME in Canada and a US experiment called STARE-2, were hit with a signal. It was a burst of radio waves so incredibly bright that it went off the charts. It was, without question, a fast radio burst. But it hadn't come from billions of light-years away. It had come from the magnetar in our own galactic backyard. This was it, the smoking gun. For the first time, we had seen the same event with both a radio telescope and an X-ray telescope. We saw a magnetar flare, and at the same instant, we saw an FRB coming from its location. It was the definitive proof that magnetars can and do produce fast radio bursts. The astronomical community let out a collective sigh of relief. The prime suspect had confessed. The 2020 burst was a watershed moment. It solved the central mystery of where FRBs come from. But, in true cosmic fashion, it opened up a whole new set of questions. For one thing, the FRB from the Milky Way magnetar was a bit of a weakling compared to the ones from other galaxies. It was thousands of times less powerful than the extragalactic bursts we see. This raises the question, are the distant, more powerful FRBs produced by the exact same mechanism, just scaled up? Or are we seeing two different phenomena? Are there normal magnetar bursts, and then some kind of hypermagnetar bursts that are far more rare and powerful? It's like knowing that both a firecracker and a stick of dynamite are based on gunpowder, but still not understanding what makes the dynamite so much more explosive. We found the engine, but we don't fully understand the throttle. The case isn't closed, it's just moved to a new, more refined phase of investigation.
And the new questions just keep piling up. One of the biggest remaining mysteries is the repeaters versus the non-repeaters. The vast majority of the thousands of FRBs that CHIME and other telescopes have detected have only ever been seen to burst once. A small but growing number of them repeat. Are these two fundamentally different types of objects, or are they the same thing, just at different stages of their lives?
One popular idea is that all FRB sources are repeaters, but their activity level changes over time. Perhaps young, hyperactive magnetars produce flurries of bursts, making them easy to spot as repeaters. Then, as they get older and their magnetic fields weaken, their activity drops off. They might only produce a burst once a century or once a millennium. So, when we see a non-repeater, we're not seeing a one-off event. We're just seeing a very old, very tired source that we are unlikely to ever catch again in our lifetimes. Another puzzle is periodicity. A few of the repeating FRBs seem to have a schedule. One famous repeater, for example, seems to switch on for a period of about 4 days, then goes quiet for 12 days before repeating the cycle. A 16-day period, like clockwork. What could cause this? It's probably not the magnetar itself. The timing is too slow. One idea is that the magnetar is in a binary orbit with another star. Its blasts might only be visible to us when it's at a certain point in its orbit, with its companion star not blocking the way. Another theory is that the bursts are always happening, but they are being channeled into a narrow beam by a thick stellar wind from a companion, and that beam only sweeps past Earth every 16 days. So while we've identified the culprit, the magnetar, we are still very much in the dark about its motives, its methods, and its accomplices. We have solved the who, but we are still working on the how and the why. Each new burst we detect adds another piece to the puzzle, revealing a phenomenon of baffling complexity and power.
Before we leave these cosmic lighthouses behind, it's worth noting one final, beautiful twist. For all their mystery, FRBs are not just a puzzle to be solved. They are also a tool, a powerful, unique tool for studying the universe itself. Remember the dispersion measure? The way the radio signal gets smeared out as it travels through the thin plasma between galaxies? That smearing is not just a clue to the FRB's distance, it's a direct measurement of all the stuff the signal has passed through on its journey to us. Every single electron that the light has encountered leaves its tiny signature on the signal. So, by analyzing the dispersion of an FRB from a known distance, we can effectively weigh the universe. We can measure the density of the intergalactic medium with incredible precision. This has helped solve a long-standing cosmological problem known as the missing baryonic problem. We know from our models of the Big Bang how much normal baryonic matter, protons, neutrons, the stuff that makes us, there should be in the universe. But when we looked at all the stars and galaxies we could see, we could only account for about half of it. So where was the other half? The answer, confirmed by studying FRBs, is that it's hiding in plain sight. It's in the impossibly thin, almost undetectable web of plasma that connects galaxies, the cosmic web. FRBs, as they travel through this web, allow us to see it and measure it. The missing matter wasn't really missing. It was just too diffuse for us to notice until we had these brilliant, brief flashlights to illuminate it. So these phantom signals, these millisecond-long shouts from across the cosmos, have gone from being a bizarre astronomical mystery to one of our most valuable cosmological probes. They are a gift from the deep universe. Now our journey takes its final turn. We have looked at hidden forces, vast emptiness, ancient light, and flickering stars. We've listened to signals from across the universe. For our last anomaly, the mystery comes to us. A physical object, a traveler from another star system that passed silently through our home, was seen for just a moment and then vanished forever, leaving behind a string of questions that may never be answered. Our final anomaly, number 6, is the silent visitor, Oumuamua.
October 19, 2017. At the Haleakala Observatory in Hawaii, a robotic telescope named Pan-STARRS was doing its nightly duty, scanning the sky for near-Earth asteroids and comets, the kind of space rocks that could pose a threat to our planet. It's a vital but repetitive job. The telescope takes a picture of a patch of sky, then another a few minutes later. Software then compares the images, looking for any dot of light that has moved. On this night,
The software flagged something. A faint, fast-moving object. At first, it seemed like just another small asteroid, but as astronomers tracked its trajectory over the next few days, they realized something was deeply wrong. It was moving too fast, way too fast. About 26 kilometers per second. That's well above the escape velocity of our solar system. And its path wasn't a gentle, closed ellipse, the kind of orbit that keeps an object bound to our sun. Its path was a sharp, open hyperbola. The conclusion was inescapable. This object was not from around here. It was not a member of our solar system. It was just passing through. It had fallen in from the vastness of interstellar space, swung around our sun, and was now heading back out into the void, never to return. It was the first object ever detected by humanity that we could definitively say came from another star. The discovery was electrifying. We had long theorized that such objects must exist, but we had never seen one. The object was initially given a technical designation, A/2017 U1, but it deserved a better name. The team in Hawaii gave it one from the local language. They called it Oumuamua. It's a beautiful name that can be roughly translated as a messenger from afar arriving first, or more poetically, scout. A scout, a messenger. The name was perfect. A piece of another star system had just shown up on our doorstep. The scientific community scrambled. This was a once-in-a-lifetime opportunity to study a piece of interstellar real estate up close. Every telescope that could be brought to bear was pointed at this faint, rapidly fading point of light. The race was on to figure out what it was before it disappeared forever. The clock was ticking. Oumuamua had already made its closest approach to the sun back in September and was now speeding away from us, heading out of the solar system at a blistering pace. It was already faint, and it was getting fainter with every passing hour. Astronomers had only a couple of weeks to learn everything they could about this mysterious visitor. One of the first things they tried to do was get a spectrum of its light. By breaking down the light from an object into its component colors, you can learn what it's made of. The spectrum of Oumuamua was featureless. It was reddish in color, similar to some asteroids and comets in our own solar system, but there were no clear absorption lines to indicate specific minerals or ices. It was disappointingly uninformative. More puzzling was the lack of a coma. A comet, when it gets close to the sun, heats up. Its ices turn directly into gas, creating a fuzzy, glowing atmosphere around the nucleus, which we call a coma, and a long tail of dust and gas. Astronomers looked very, very closely at Oumuamua for any sign of a coma or a tail. They saw nothing, absolutely no hint of outgassing. This was a crucial clue. It suggested that whatever Oumuamua was, it was not an active comet. It seemed to be a dry, inert piece of rock, like an asteroid. But then came the next piece of the puzzle, and it's the one that elevated Oumuamua from a curiosity to a profound anomaly. As they tracked its brightness over time, they found that it was changing dramatically. It wasn't just a steady point of light. Its brightness was varying by a factor of 10 every 7 to 8 hours. There's only one way to explain such a huge variation in brightness. The object's shape must be extreme. It couldn't be anything close to a sphere. A sphere, as it tumbles, always presents roughly the same surface area to us, so its brightness remains constant. To have its brightness change by a factor of 10, the object had to be incredibly elongated. It had to be long and thin like a cigar, or flat and wide like a pancake. As it tumbled end over end, we would see its broad side, maximum brightness, and then its narrow side, minimum brightness. The math suggested a shape that was at least 5 and maybe even 10 times longer than it was wide. No asteroid or comet in our solar system has a shape anywhere near that extreme.
So our profile of the visitor was getting stranger. It came from another star. It was small, probably a few hundred meters long. It was dark red. It had no visible coma or tail. And it had a shape more extreme than any object we had ever seen in our own solar system. a cosmic cigar or pancake tumbling through our home. This was already strange enough, but the final piece of data, the one that broke the camel's back, was yet to come. As astronomers continued to track Oumuamua's position with incredible precision using the Hubble Space Telescope, they found something that made absolutely no sense. It was deviating from its path. After it whipped around the sun, it started to speed up. It was accelerating away, pushed by some gentle, unseen force. This is called non-gravitational acceleration, and it's not by itself a mystery. We see this all the time with comets. As a comet is heated by the sun, the jets of gas erupting from its surface act like tiny rocket thrusters, giving the comet a gentle push that can alter its trajectory. This is standard comet behavior. But Oumuamua wasn't a comet. We had looked. We had seen no coma, no gas, no dust, no tail, nothing. It was accelerating without any visible means of propulsion. It was a stealth rocket. This was the core of the anomaly. You can't have it both ways. An object can't be an inert rocky asteroid in its appearance, but act like a gassy propulsive comet in its motion. Something was very wrong with this picture. This single fact, the acceleration without outgassing, blew the mystery wide open and led to a flurry of theories, each more exotic than the last. Scientists had to find a way to explain a force that could push an object, but that would be completely invisible to our telescopes. The simplest explanation was that it was outgassing, but the gas was made of molecules that we just couldn't see, like pure hydrogen or nitrogen. Maybe the dust particles were too large for us to detect. These were plausible ideas, but they required Oumuamua to be a very new, very strange kind of comet that we had never imagined before.
Let's dive into those invisible rocket theories. The most popular one for a while was the idea of a hydrogen iceberg. The theory, proposed by two astrophysicists, suggested that Oumuamua was a giant frozen chunk of solid hydrogen. Hydrogen is the most abundant element in the universe, and in the coldest, densest parts of giant molecular clouds, it's theoretically possible for it to freeze into a solid iceberg. This was an ingenious idea. As a hydrogen iceberg got close to our sun, the hydrogen would boil off, creating the gentle thrust needed to explain the acceleration. And because hydrogen gas is transparent, the outgassing would be completely invisible to our telescopes. It seemed to solve everything. But the theory had problems, big problems. For one, solid hydrogen is incredibly fragile. A hydrogen iceberg traveling through interstellar space for millions of years would be eroded away by starlight and cosmic rays. It's unlikely it would survive the journey. Furthermore, no one is sure if hydrogen icebergs can even form in the first place, let alone grow to be hundreds of meters long. The theory was clever, but it seemed to be on shaky physical ground. A more recent and perhaps more plausible theory is the nitrogen iceberg model. This idea suggests that Oumuamua was a chunk of frozen nitrogen knocked off the surface of an exo-Pluto-like exoplanet in another solar system. We know this can happen. Pluto, in our own solar system, has a surface covered in glaciers of frozen nitrogen. If a giant impact were to hit an exo-Pluto, it could send fragments of its nitrogen ice crust flying out into interstellar space. This theory works a bit better. Nitrogen ice is far more durable than hydrogen ice, and when it's heated by the sun, it would produce invisible nitrogen gas, explaining the stealthy acceleration. It even explains the weird shape. As the iceberg traveled, it would be eroded by cosmic rays in a way that would naturally flatten it into a pancake-like shard. The nitrogen iceberg theory is currently one of the leading natural explanations for Oumuamua's bizarre behavior. It's still an exotic object, a piece of a distant world unlike anything we have in our own system, but it's a possibility that doesn't break the laws of physics,
But it's not the only possibility that was put on the table.
When you have an object that accelerates without a visible engine, you are eventually forced to consider the possibility that the engine is real, just not natural. This brings us to the most famous, most controversial, and undeniably most exciting theory about Oumuamua. The theory championed by Harvard astrophysicist Avi Loeb. His proposal was simple and stunning. Oumuamua was not a rock or an iceberg. It was an artifact, a piece of technology from another civilization. Loeb argued that all the natural explanations for Oumuamua required us to believe in an object of a type we have never seen before: a hydrogen iceberg, a nitrogen shard, a 10-to-1 aspect ratio asteroid. He asked a simple question: if we have to invent a new class of object to explain it, why not consider the possibility that it's a class of object we have already theorized about, but have not yet seen? Specifically, a solar sail. A solar sail is a proposed method of spacecraft propulsion. It's a large, thin, lightweight membrane that uses the pressure of sunlight itself to move. The photons streaming from a star have no mass, but they have momentum. As they strike the sail, they transfer that momentum, giving the craft a tiny, gentle, but continuous push. No fuel needed, no engine exhaust, just the light of a star. A craft powered by a solar sail would accelerate away from a star with no visible outgassing, just like Oumuamua did. Furthermore, a solar sail would need to be very thin and wide to be effective. This could explain the extreme light curve. If Oumuamua was a technological sail tumbling end over end, it would naturally produce the dramatic changes in brightness that we observed. The theory seemed to fit all the bizarre facts remarkably well. The shape, the acceleration, the lack of a coma. It was a neat, if mind-boggling, package. Loeb suggested it could be an active probe, or perhaps a defunct piece of technology, a bit of space junk from another culture, drifting silently between the stars for millions of years.
The solar sail hypothesis was and remains highly controversial. The scientific principle of Occam's razor suggests we should prefer the simplest explanation that fits the facts. And for most scientists, inventing a new, exotic type of natural object, like a nitrogen iceberg, is considered simpler than invoking an alien civilization. The bar for an extraordinary claim like "we've found alien technology" requires extraordinary evidence, and the data for Oumuamua, while strange, is too sparse to be considered definitive proof. The debate highlights a fascinating tension in science. On one side, you have caution and skepticism, a refusal to jump to fantastic conclusions without irrefutable evidence. On the other, you have a willingness to consider all possibilities, especially when the normal explanations seem strained. Avi Loeb argues that to reflexively dismiss the possibility of an artificial origin is a form of terrestrial arrogance, a failure to imagine that we might not be the only technological species out there. Most of the astronomical community remains unconvinced. The nitrogen iceberg theory, or something like it, is generally seen as the more likely, if less exciting, answer. But no one can deny that Oumuamua stretched our definitions of what a natural object can be. And then, just as the debate was raging, a second interstellar visitor arrived. In August 2019, an amateur astronomer named Gennady Borisov discovered a new object entering our solar system. It was given the designation 2I/Borisov, the second interstellar object. And it could not have been more different from Oumuamua. 2I/Borisov looked and acted perfectly normal. It had a huge, visible coma of dust and gas. It had a beautiful tail. Its spectrum showed familiar chemicals like cyanide and diatomic carbon that we see in comets in our own solar system all the time. It was, without a doubt, a comet. A completely, utterly, and wonderfully boring interstellar comet. And the discovery of this perfectly normal visitor did something remarkable. It made Oumuamua look even weirder. It proved that normal interstellar comets do exist, and this is what they look like. And whatever Oumuamua was, it was not that.
We will never get a second look at Oumuamua. It is gone. It is now far beyond the orbit of Neptune, hurtling out into the deep dark at incredible speed, forever beyond the reach of our telescopes. We had a window of just a few weeks to study it, and that window has closed forever. We will almost certainly never know for sure what it was. And perhaps that's the point. Oumuamua's legacy is not in the answers it gave us, but in the questions it forced us to ask. It was a wake-up call. It proved that the space between the stars is not empty. It is a thoroughfare. Objects are constantly being thrown out of their home star systems and sent on billion-year journeys across the galaxy. And for the first time in human history, we are now able to see them as they pass by. Oumuamua was the first, but it will not be the last. With new, more powerful observatories like the Vera C. Rubin Observatory coming online soon, we expect to find many more interstellar visitors in the coming years. Will they all be boring comets like 2I Borisov? Or will we find more strange ones, more Oumuamuas, that challenge our expectations? Every new visitor will be another piece of a distant, unknown solar system, delivered right to our doorstep. Each one will be a messenger, carrying clues about how planets form and how solar systems evolve elsewhere in the galaxy. And if we ever do find one that is unambiguously artificial, that discovery would, of course, change human history forever. But even if they are all just rocks and icebergs, they are still profoundly important. Oumuamua was a scout. It was a fleeting, silent messenger that delivered its message not with words, but with its mere presence. The message was simple. The universe is a bigger, stranger, and more interesting place than we have ever imagined. And we should keep watching the skies, because you never know who or what might be dropping by next.
And so, our journey through the cosmic zoo of the strange is drawing to a close. Let's take a breath and look back at the path we've traveled tonight. We started with a feeling, an unseen force. We learned that our entire galaxy is a leaf in a cosmic river flowing towards the Great Attractor, a vast gravitational valley we call Laniakea. We saw how the most powerful structure in our neighborhood could hide from us for so long, concealed by the dust and stars of our own home. It was a lesson in perspective, in realizing the true scale of our cosmic address. From the ultimate something, we traveled to the ultimate nothing, the Bootee's void, a place defined by its profound, soul-crushing emptiness. We floated in a bubble of nothingness hundreds of millions of light years across, and wondered what it would be like to live in one of its few, lonely galaxies, staring out at a sky almost entirely devoid of neighbors. It was a lesson in isolation and the lumpy, uneven texture of creation. From a hole in space, we moved to a hole in time. We looked at the CMB cold spot, a mysterious cold bruise on the baby picture of our universe. We asked if it was a statistical fluke, a window into another universe, or the shadow of a colossal supervoid. It was a lesson in origins, in the faint clues left behind by the dawn of time itself. Then our gaze collapsed from the universal to the specific. We stared at Tabby's star, a single, unassuming sun that flickers and dims in a way that defies all easy explanation. We entertained plagues of comets, and even the ghostly presence of alien megastructures, all to explain a light curve that simply shouldn't exist. It was a lesson in humility, a reminder that even a single star can harbor a mystery that stumps us completely.
From a star that wouldn't behave, we turned our ears to signals that shouldn't exist. We listened for the fast radio bursts, those millisecond-long shouts from across the universe, each one carrying the energy of a sun. We followed the detective story, from their accidental discovery to the revelation that their source is likely a magnetar, a city-sized stellar corpse with a magnetic field of unimaginable power. It was a lesson in the sheer violence and energy of the cosmos. And finally, the mystery came to us. We watched the passage of Oumuamua, the silent visitor from another star. A tumbling, cigar-shaped or pancake-flat object that accelerated without an engine. We weighed the possibilities, from nitrogen icebergs to alien solar sails, and were left with more questions than answers as it sped away, back into the interstellar night. It was a lesson in the unexpected, a reminder that we are not isolated, but are part of a galaxy where things travel between the stars. The Great Attractor, the Boötes Void, the Cold Spot, Tabby's Star, fast radio bursts, Oumuamua, 6 anomalies, 6 postcards from the edge of understanding. They are all different, yet they all share a common thread. They are the glitches in the matrix, the data points that don't quite fit the curve. They are the universe refusing to be simple, refusing to be neat. They are the loose threads that, when pulled, can unravel our neatest theories and force us to weave a new, more intricate tapestry of knowledge. They are, in short, the best part of science. They are the engines of curiosity.
So what is the takeaway from all this strangeness? It can be tempting to look at these deep mysteries and feel a sense of unease, a feeling that our grasp on reality is fragile, that the universe is a chaotic and incomprehensible place. It's easy to feel small and insignificant in the face of such vast, unsolved puzzles. But perhaps there is another way to look at it. Perhaps the goal isn't to solve everything. Perhaps the universe isn't a final exam that we are supposed to ace. Maybe it's more like a piece of music or a work of art. You can analyze its structure, its harmonies, its brushstrokes, and that analysis can deepen your appreciation. But at the end of the day, you don't solve a symphony. You experience it. You let it wash over you. You allow its beauty and its mystery to coexist. Each of these anomalies is a strange and beautiful note in that cosmic symphony. The deep, resonant bass note of the Great Attractor's pull, the profound, sustained silence of the Boötes Void, the chilling, high-frequency dissonance of a fast radio burst, the playful, unpredictable melody of Tabby's Star. They are not mistakes or errors in the composition. They are the composition. The complexity is the point. The comfort, if you're looking for it, is in the knowledge that the story is still being written. We are living in a golden age of discovery. Every new telescope, every new survey, every patient observer staring at a screen is adding a new sentence to the book of our understanding. We may never reach the final page, and that's okay. The joy is in the turning of the pages. The peace is in knowing that there will always be another mystery tomorrow. Always another dark corner to illuminate. Always another postcard from the edge, waiting to be read.
And so, as we settle back into our own familiar corner of the cosmos, let these mysteries be a source not of anxiety, but of peace. The universe is under no obligation to make sense to us. It is vast and ancient and wonderfully, stubbornly weird. It has no interest in our deadlines or our desire for neat, tidy answers. And in that fact, there is a strange kind of liberation. It means we can let go of the need to have everything figured out. We can simply float in this quiet moment and appreciate the magnificent scale of our own ignorance. We can find a strange comfort in the unknown. The questions are, in many ways, more beautiful than the answers ever could be. So let the Great Attractor pull you gently towards sleep. Let the silence of the great nothing quiet your mind. Let the steady, patient rhythm of scientific discovery be a soothing balm. There are mysteries out there. There are puzzles we may never solve. And that is a wonderful thing, because it means the journey is far from over. It means there is always, always more to explore. Now, just close your eyes. The story will continue, with or without us. Sleep well.